Well, hello everyone, and welcome to a new video. In this video, I'm going to be talking about OpenMP, using OpenMP with C++. So this is like part 2 of parallel computing. Now, in the first part, I stopped at a point where we were talking about race condition, and a race condition will happen when multiple threads will try to have access to the same shared variable or shared data. So when there's a level of dependency and two threads are trying to have access to the same variable at the same time, you'll end up having results that makes no sense or are not correct. So in this case, as you can see here, I do have a for loop that will go all the way to this big number. And then after that, I'm just going to have a counter that's going to add 1. So basically, by the time I'm done, I'm supposed to get a value as big as this value. But when you use multiple threads, that's not the case. Let me start with 8 threads. And when I run the program, since the number is too big, so the for loop is taking a little bit while, but this is the number we got. And the number here is like very, very close to dividing this big number by 8. You get something very close to this one. Now, of course, if I go ahead and why is that happening? Why I'm not getting the right result? Because at a certain times in those for loops, 8 threads are trying to update and increase count by 1. So imagine count was equal 10 at that point. So 10 of those threads are trying to increase it to 11. So it looks like the same variable is going to be increased to 11 for 8 times. So it's going to be 11 and 11 and 11. It's not like it's going to go 11, then 12 and 13 and 14. No. It's going to happen that all these threads are going to change it at the same time. So by the time those 8 threads are done, the final value of the count is going to be 11 instead of going all the way to 19 or something. So let me just go ahead and show you what's going to happen if I got 4. Of course, the time is still long, but the number is a little bit bigger than the previous one. And again, if you take that number that I have here and divide it by 4, you'll get something closer to this value. Now, let me show you what's going to happen if I have 2 threads. And I want you to notice here, and here's the number. Look at this number. This number is very close to, if we take this value here and divide it by 2, you'll get something very close to this number here. The whole point here is basically 2 threads are trying to have access to the count variable at the same time, and as a result, it looks like half of the iteration has been going through. Now, look at this. What if I have 1 thread? Look at the results in this case. And here it is. It's exactly the same number. So this would tell you what is multi-threading means exactly. When you have multiple threads are trying to have access to the same variable at the same time, this is what we mean by a race condition. So this is the problem that we talked about, and now we need to figure out how to find a solution for that. But before we get into that part, I just want to make sure a few points here before I continue. Number 1, if you want to get the maximum number of threads allowed by your system, you have this statement here. You can create an integer. You could call it t, for example, and you can say OMP get max threads. This will tell you how many threads your processor can run at the same time. And then you can use t here. Just in case you don't want to use numbers, you want to use whatever is allowed in your system, you can do that. Now, I just thought about mentioning that. Now, let's just go back to another problem that we have with multi-threads, which is the timing. Now, this is something you need to understand very, very clear. Multi-threading will not magically improve the performance of the system. There is a lot of conditions that need to be available, or situation that need to be available for your system to be able to take and get some benefits of multi-threading. And just to give you an idea about this, I'm going to show you this example. Now, this here will measure the time, this statement here will measure the time at the beginning of the execution, and this one is going to measure the time at the end of the execution for this segment of code. And then by subtracting the end from the start, this should tell you how long did it take for this part to be executed. Now, what I'm going to be doing, I'm going to test the following. I'm going to test if there is no threads at all. I didn't create any threads. And then I'm going to measure with 1 thread, and then 2 threads, and 4 threads, and 8 threads. And let's see what time we're going to get for each one of those cases. I'm going to write it down on a piece of paper, and then we're going to discuss about that, and we'll see what we're going to get. So let me run this first. And here we go. So when I don't use parallelism at all on OpenPM, I get 1.981. Okay, let's go ahead and remember that number. Now let me take this away. I'm going to use multi-threads, and now we'll start with 1. Which basically is supposed to be the same thing as the previous one, because when I said no thread, it was, there is 1 thread actually. But here I used multi-threading, and this time it's 2.209. So this is 1, this is 1, 2, but using OpenMP. And now let's go to 2, and then 4, and then 8, and see what we're going to get as we increase the number of threads. So let's go with 2 now. The reason I'm using a big data, the size for number of iterations, so it will consume some time. And look at this, 3.274. That's 2 threads. You see the number is increasing now. Now let me just put 4. Let's see. And now it's 3.46566. And finally, let's go and see if I have 8 threads. And now it's 3.41. Well, this one looks like it's a little bit better comparing to the 4. A little bit of improvement anyway. But again, you cannot compare that to 1 thread, or comparing that to 2 threads, or compare it to no threads, because with no threads I get 1.99, and then with 1 thread using OPN it was 2.2. But again, as I increase the number of threads, the number usually increases. Now the question that we need to ask ourselves, well, it looks like increasing the number of threads didn't improve that much for us. And the answer will be yes, that's true. But the thing that you should know is using multi-threads includes a lot of behind-the-scene process that you don't see. That by itself adds on to the time of conception when you want to process any data. So what they say usually, if you're going to process, let's say, a small size of data, and if you want to go and use multi-threading with it, you will not see any improvement, because there's a process of creating those pool of threads and synchronizing them, and a lot of more details that OpenMP is trying to hide from us. So all this time is going to be added to the total time of execution, and that will make the process a little bit longer. Now, they said in the reference that I read is when you increase the size of the data that you're processing to a really huge amount of numbers, you will see improvement in the performance with increasing of the threads. So that's something that I try to use here, but every time I try to create an array with a big size, I got it out of memory, types of errors, so I couldn't actually demonstrate it here in my system. But the idea here is when you have a lot of data, or a huge amount of data to process with multi-threading, you might be able to see some improving using multi-threads. But that's not the case always. There's another thing that you have to put under consideration, which is multi-threads use shared memory. And because they use a shared memory, that basically means we may end up having the race condition. And because we have the race condition, we're not going to get the right answer for the result, so we need to find solutions. The solution basically will slow down the fact that you can have multiple threads to execute the same or the multiple instructions at the same time. So this here is just to demonstrate that you should not expect multi-threading to give you a magic solutions. You should understand this. If you have a processor with multiple cores, and then each thread will have access to a different amount of data, or if not shared data, you may see some improvement in the performance overall. But traditionally, it's not really easy to see improvement just by having multi-threads that's going through the same array or through the same for loop. Now, with that being said, let's go ahead and start talking about the solutions for what they call it, the erase condition. So what I'm going to do, I am going to keep this here, and I'm going to take this one away. I don't need this. And I don't need this. I'm going to upload this file, of course, later. So let's see here. What do I have? I have 8 threads. I'm just going to go with 8 threads. Now, if I run this, let me reduce the size here so the program will execute faster. Let me just make it 1,000. So we know that the result should be 1,000. But we're not getting... Oh, actually, it is 1,000. Let's see what's going to happen here. Am I using any threads here? Yes, I am. Oh, let's increase it a little bit. 100,000. Okay, now I'm seeing some problems. Okay, let's make it 1,000,000. And here we go. So, how do we solve this problem? Well, there is a solution for that. Actually, there are 4 solutions to solve the what they call the race condition. And those solutions, basically, we call them synchronization process. We have 2 types. We have the process synchronization. We have the data synchronization. If you want to think about it like this, all of those threads, when they execute separately, independently. But when it comes to the time where they need to have access to a shared memory, this is where they have to go and wait in line and go one by one. Because if you think about it again, executing any threads, it's not a simple process. It's a complicated process. So to execute a thread, we will go parallel in every single step in the process, except the part where there will be access to a shared memory. Whenever there's access to shared memory, we use what we call a shake hand procedure, where every single processor or thread will work with the other threads to make sure that the access to that shared memory is going to go in a sequential form. And with that being said, we do have those 4 solutions. We have atomic, we have critical, we have locks, we have reduction. Now, each one of them comes with advantage and disadvantage. The table here shows those advantages. First of all, atomic is faster. It only can have 1 statement, not a block of code. So atomic only accepts 1 statement. And it's a type of data synchronization, because here it says we have 2 types. We have a data, we have a process. Now, let's go to the critical. Critical is a little bit slower than the atomic, but it accepts multiple statements instead of a single statement. So here we go. You got those 2 solutions. One of them is faster and the other one is slow. We know that atomic only have 1 statement. If you have multiple statements, multiple data you're sharing, trying to have access to, then you're going to have to go with critical. Also, we got locks. Locks is a little bit, it's faster, okay? It's multiple, so it looks like it's good so far. This, it just has some problems when it comes to the syntax of it. It's not easy to write. It has many steps, if you will, that you have to go through. So those 2, you'll see that really easy. But when it comes to locks, the process to create that or to use locks is a little bit more complicated and longer than those. And you can easily make some mistakes there. Reduction is also usually another option that we have. It's a little bit slower comparing to the other ones. And also, it comes with 1 statement. So what I'm going to do, I'm going to go one by one to show you how do we use them. So let's start with the first one, which is the atomic. The atomic is very simple. Now, let's look here to this portion of code. We know that this is the part where the problem is happening every time we're trying to update the account variable. So what do? We come here and we type pragma, and then you type OMP, and then atomic. And then you're done. Okay? So this, by typing this statement here, we're basically defining that this statement here is an instruction where a race condition is happening. So we don't want that to happen here. So we should get the right answer. And here it is, with no problems. And of course, I can increase this as much as I want, and I'm still going to get the same results. So again, just remember here, having 8 threads, trying to update this count, you cannot look at the whole process as a one simple operation. It's a lot of complicated operation that's happening inside your CPU. Now, all these operations are done in a parallel form, except the part where they're trying to have access to the count. This is where you're going to work in a sequential form, where each one of them need to make sure that each one is going to take its turn to have access to that value in that sequential form. So this is, again, what we mean by atomic. Now, when it comes to critical, all you have to change the word here, critical, atomic to critical, and then you're going to have to open a curly brace, and then you're going to have to close it. Let's run this and see what's going to happen. I knew it. There was a problem going to happen. I think I should go like that. And no, let's see what's going on here. Critical. Of course, I'm missing an I here. Let's run it again. No, he doesn't like it. I remember there was an issue with the critical. And here it is. Look how long it took comparing this to the atomic. Atomic was able to get the whole thing done without the need to wait. But critical, it took it way too long. Now, just let me show you. I'm going to run it again. 1, 2, 3. I almost got to 3. Now, let me take this away and take this away and convert this to atomic. One. Here it is. I didn't even complete the one. So you can see here when it says the atomic is faster, well, actually it is faster. Now let's go ahead and talk about reduction. Reduction basically will work in a different way. I'm going to take this one away. In reduction, what we used to do, we need to come here in the same statement where we define the pragma open parallel for minimum. You come for num threads, you come in this area and you type shared. Reduction, my bad. And you open a parenthesis, and you're going to have to tell me what is the operation that you are applying the operation to, which is plus plus, and then you can come here and say count. Now, the problem is plus plus is not supported in this reduction. We have a list of operations that we can apply. So we can apply plus. Since that's the case, I could come here and say plus equal 1 if I actually want to use it. So you can see here, reduction, you have to put the operation, and you have to put the variable that you're going to actually apply it to. Let's see if this is going to work with no problems. Oops, he didn't like it. Let's see, what is the problem that you don't like here? Line number 12. Well, I am reduction. Oh, sorry. This is supposed to be a colon. Let's give this a try again. And here it is. As you can see, it's kind of fast. So there's no problem with that technique as well. So we saw the 3 techniques. We saw the atomic, critical, and reduction. And you can see here the problem with the reduction, that you're going to have to actually write this statement here, which, again, could not be a big deal. We also had to write a pragma here. But the problem is here that you need to specify what is the operation and what is the variable that you're going to apply that, whereas the race condition is going to be applied. Now, the locks basically is my least favorite one because it goes through a lot of steps, and I am going to show you those steps now. Let me take this away. So at the beginning, you have to come here and start with this statement. OMP underscore lock underscore T, and there's a right lock, and put semicolon here. And then after that, you're going to actually initialize the lock. So OMP underscore init lock, and you're going to use a reference for this object here. Okay, and of course, you're going to have to put a semicolon as well. And then the part where you are going to do and apply, the part where the race condition is going to apply, you have to set the lock. So we'll go OMP underscore set underscore lock. And then just like we did here, you copy this, you put it here. You put semicolon here. This is how you set it. And then you're going to have to unset. So I'll kind of copy this and put it down. And then just put unset here. And then after that, you're going to have to destroy once you're done. Where's the end of this? Well, I'm going to assume this is the end of it. So you're going to have to destroy it. Let me just copy this. Oops. Copy this. And let's put it here. And then remember, you're going to have to destroy it. So let's type destroy here. And I should be done at this point. So you can see here the lock is a little bit complicated. It's 1 line, 2 line, 3 line, 4 lines, 5 extra lines just to be able to do that. Let me just run it. And oh, look at that. Fatal error. Oh, this is new. Let's see what's going on here. What's the problem? I'm pretty sure I'm using the right syntax. Let me see if I can actually fix this. If I come here and put this part here, where's the destroy? Let me close it here. Let's try and see if that's going to fix it. Oh yeah, that fixed it actually. And here it is. So this for loop, even though it just contained one statement here, but you're going to have to actually have the curly braces. So those are the 4 lines. As you can see here, you can use multiple statements here, of course, if that's the case. It's better than critical. But again, it's a little bit more complicated because it contains more lines to write, and that's the biggest issue with those conditions. Now, so you have those 4 cases, and those 4 cases basically would tell you how do you solve, sorry, those are 4 solutions on how do you solve the problem of race condition. There's another way to use parallel computing using OpenMP. You can create a pragma of sections, and then you will define multiple sections, and each section there will be running in parallel by thread. So what do I mean by that? I don't want to erase this. Well, since I'm gonna upload the video, so you should be able to look at the code if you want to. What I'm gonna do, I'm gonna take this out just to show you another example of different ways to handle multi-threads. I'm not gonna go into details, but I'm just gonna show you. And here it is. So look at this. This is the parallel sections. This is the beginning of it, and this is the end of it. Now, in this area here, between the open and the close, you can have a pragma OMP section, pragma open section, pragma OpenP section. So you're going to have multiple sections. In each one of those sections, you can create a piece of code. Not like, let's say, a segment of code. And what's going to happen, basically, each section is going to be treated as a thread, is going to be implemented as a thread, and this is going to be implemented as a thread, and you can get them all done at the same time. You can have as much, of course, as you want from those threads. So remember here, this area here, it could be a block of code that will do something. This will be another block of code that will do something else. You can have a third one will do something, and you can guarantee that it's not going to go like step by step. You finish this, and you finish this, and you finish this. No, it's multi-threading, so all of them are going to work at the same time. So that's what we mean here by parallel sections. Now, with that being said, I can show you some examples of how do we use OMP to solve some daily problems that we have. The first one I'm going to talk about is how do you find the indexes? Let's say you have an array and you're searching for an element inside that array. And you know that that element exists multiple times. So what I want you to do, I want you to store all those indexes in a list and send them back to me. So you're searching for an element inside an array, let's say 10, and 10 does exist in 3 spaces or 3 locations in that array. So I want to have the index of those 3 elements. The process by itself sounds like it's very easy, and I'm going to show you how do we do that in a sec. So I do have the code already created, so that will save some time. So what do I have here? Basically, I have a list. Since I'm using a list, let me just go ahead and include list. And since I'm looking for integers, so it's going to be a type of integer, I'm going to go with threads of 4 or 8. And then here it is. This is my pragma. Now, of course, I need to have a Victor here. So let's go ahead and am I using a Victor here? Yes, I'm going to be using a Victor. So let's go ahead and include a Victor. And I'm going to go ahead and create a Victor here. So Victor. Also, let's go with size type of integer. I'm going to call it Vic. And let me initialize this Victor with those values 1, 2, 3, 4, 5, 6, 7, 5, 8, 9, and then 5. And imagine we're looking for the value 5 here. So I need to come here and to replace target with 5. And then this is going to be list pushback I. Now what is he complaining about here? So I got Victor. Oh, semicolon. And here we go. So after that, if I can just print the list, I should be able to do that. So I'm going to go with a for loop. And I will say odo list. I'll say, let's say L equal list dot begin. And I will say, as long as L doesn't equal list dot end, and put semicolon here. And I'll go L plus plus. And in this area, I'm just going to go cout asterisk L. And let's put a space here, semicolon. Okay. So let's see how is that going to work. I'm supposed to get 0, 1, 2, 3, 4, and then 5, 6, 7, 4, 7, 8, 9, 10. So let's run this. Hopefully, here it is, 4, 7, and 10, as you can see. Again, this is very straightforward. Instead of having a regular for loop, I just decided to go with multi-threading to get the job done. Of course, again, if you're going to go measure the time with a single thread or a multi-thread, I don't think you're going to see any improvement for the reasons I mentioned before. Let's see here. What else do we have? What if I want you to find an item, the first appearance of an item, inside a Victor? So I don't need a list. Let me just take that list away. So I don't need a list. And instead of actually pushing back a list, now this is important actually. I'm just going to come here and say, the moment you find a match, I want you to, let's say, cout I, end line semicolon, and then break. And this is where I have a problem. A break statement. You are never allowed to have a break statement inside a for loop that is a part of a pragma of OMP. This is a problem. You're not allowed to do that. So let me run this, see what's going to happen. Should give me an error. No, actually it didn't. But look at the value that it gave me. 7104. Where's that number coming from? And it gives me multiple end lines at the same time. You know what I'm going to do? I'm going to do something different here. I'm just going to come here and say, wait a minute, I think this is for the for loop and this is for yes, if its name is what I'm going to say. I'm going to come here, for example, say index, integer, index equals 0. And I'm going to come here and say ind equal I, and then break. And then here I'm going to come and say show me index, cout ind, and line semicolon. Let's run this. And it gives me 10. Well, 10 was here. Let me just move 5 here and move 9 here. Let's run it again. And now it's 4. Well, that's weird. 0, 1, 2, 3, 4. So you see here, it's not really doing the job that it's supposed to do because of this break statement. You're not allowed to have a break statement inside a for loop. That's what you should know. So let me take the 4 away and see what's going to happen now. And I got 9. Now it makes more sense. Let me just change this one and put 5 here. And now we get 10. So it's going to show me the last appearance of that variable, the index of the last appearance for that value that I'm looking for. So that's how it works. If you want to actually see the first appearance of that letter, you're just going to have to switch the way you search in that loop. Instead of starting from I, start from the sides and go from right to left. You're not allowed to have a breaks inside an OpenMP. That's what you should know. I guess I am going to stop at this point, and we do have more examples you can have a look at inside the PowerPoint that's going to be posted. If you have any questions, of course, let me know, but this is the end of the parallel computing section. Parallel computing section is it's not one of the easiest topics to cover, I'll be honest with that, because of the amount of details that comes with it and the amount of things you have to put into consideration to be able to see. Like I remember when I start reading about the parallel computing, I spent a really long time just trying to find out if there's any way I can show an improvement in something that I'm calculating using the OpenMP, just to prove that there is a point of all of this. And then I couldn't, and I did a research to understand why is that impossible. And it turns out there's a lot of details behind the scene that you don't see. One of them, as I said, there's a process of creating a pool of threads every time you want to use OpenMP. And there's a process of synchronization of these threads, which takes time. So if you put the time of creating the threads and the synchronization of these threads, all of that will add up to the time of the execution of the data, and you end up actually having to spend more time than if you just go with a single thread. And for that reason, they said OpenMP will be good or better if you actually use it with a big amount of data. And then I was like, okay, let me try to see if I can use it with a big amount of data. I did find a way to use it with a big amount of data, and still I couldn't find an improvement, a huge improvement in the time consuming. So I did another research to find out. They said, even though you were able to perform the multi-threading, but just the fact you have access to some shared resources, that by itself will reduce the efficiency of multi-threading. And basically they said if you want to get the best out of multi-threadings, it's basically if you can have each thread to have its own resources without using anything shared. That way you can see some improvement when it comes to multi-threading or parallel computing. Okay, so I am done for today. Thank you for watching, and I'll see you guys later.